Uh, so I just started the recording. Do you see me? Do you hear me now?
I can hear you now.
Okay, very good.
Yeah.
So yeah, once again, today is lecture number 7, I believe. And let's quickly recap what we've done last time. Okay, so last week we started with an example of a density matrix of one single qubit in a pure state. Okay, so as we discussed several times, the general pure state of a quantum qubit is given by the superposition of two basis vectors with corresponding coefficients. So C0 state 0 plus C1 state 1, where states 0 and 1 are basis vectors. They are orthogonal. That's why we can decompose any vector in this two-dimensional Hilbert space using these two vectors. And by definition, the density matrix is given by this equation. It is basically a sum up of all the different states in the classical probability theory meaning. Okay, so this P here with the index I denotes the probability of finding a system in some state I. Like if you have many different qubits, with you can measure or detect one of them or pick up one of them with some probability. Okay, like blue, green, yellow, you have mixture of them and you get a particular one with some probability. In our case, we discuss now, we have only one qubit, so the density operator is represented in this form, which is fair for any pure state. Okay, and we have calculated the density matrix in this form, which is given by basically the combinations of the C elements, C terms in the superposition. So these elements C0 absolute squared, C1 absolute squared represent the probability of finding the qubit either in the excited state 1 or in the ground state 0, and C101 density matrix elements, they give the quantum interference of the two. So basically these two elements, they allow the states interfere or interact. Okay. Then we also discuss the density matrix for different different systems, different states. Other examples on density matrix. We noted that density matrix is used when we deal with systems with decay and dephasing, which is always the case. And all systems are imperfect, right? So we always have some decay and dephasing, and decay describes the energy dissipation in the system when the qubit transit from the excited state to the ground state spontaneously, and it takes the time duration t1. Okay, dephasing is the process of losing the phase of the qubit, and is described by the duration t2 star. And this dephasing time is the main parameter of any qubit, because it basically describes the time the qubit preserves the quantum information, quantum coherence. As we will see today, all of the IBM quantum computers, they specifically indicate this T1 and T2. And T2 is, of course, always smaller than T1 because decay also contributes to the dephasing. Okay, that's why we have this framed formula for the total dephasing, T2, which is given by the decay and pure dephasing. Then we discussed how we combine the qubits to form multiple qubit systems. It is given by the tensor product operation. For example, if we have two qubits, each described by psi state vector, we combine them, and this operation is described by tensor product. Well, it's not really described. Tensor product allows us to generalize this two-dimensional Hilbert space to four-dimensional Hilbert space where we can describe the system of two qubits and so on. The system of three qubits requires the Hilbert space of dimension 8 and etc. And also, of course, the people still arrive. Of course, all the operators generalized also through this tensor product from 2 by 2 operators. They can be generalized to 4 by 4 for two qubit systems, etc. We mentioned this Bell state. Today we will see how this Bell state can be generated. Yeah, and we also discussed the concept of quantum parallelism. So the quantum parallelism means that for one single qubit, one single qubit, in contrast to the classical bit, right, which is either 0 or 1. Classical qubit, or the quantum qubit, is a system that is represented in both states simultaneously. And measuring the qubit, you can get either one with different probability. Okay, and if you have the system of two qubits and they interact, they entangled, then first of all, the dimension of Hilbert space becomes greater. For example, from 2-dimension, it's promoted to 4-dimension, and the dimension of the vectors also grows. And if you put more and more qubits, this dimension grows exponentially, 2 to the power of number of qubits in the system. And according to the principles of quantum mechanics or quantum physics, if the qubit can be in either state, you need to take into account the existence of both. Before you measure the qubit, you consider the qubit being in both states. And the same works for system of 2 or 3 qubits. Before you measure them, you have to take into account all these possibilities, which is exponentially large number for a large number of qubits. Okay, and This allows you to explore a huge number of possibilities at the same time in one single run. Okay, we will discuss that soon. And we have started the new chapter about quantum gates and logic. And the first subchapter was about the Bloch sphere. Okay, so the Bloch sphere allows us to basically introducing the angles theta and phi, the concept of the Bloch sphere, which is, by the way, the sphere of radius 1, okay, allows us to represent any state of a single qubit by a point on a sphere of this, on the surface of this Bloch sphere. Okay, and then we define the poles, all the 6 poles of this sphere, and all the 6 poles of this sphere. We've got a question in the chat. Why doesn't IBM use the Bloch sphere? Yeah, they don't use the Bloch sphere because Bloch sphere works only for one single qubit. Quantum computing requires multiple qubits. Okay, so in some sense, Bloch sphere is useless for quantum computing. I mean, honestly, even the representation that IBM uses also kind of not really useful for quantum computing because it becomes too complex. But at the same time, Bloch sphere allows you to represent nicely all the states of a qubit. Okay, and that's why we discuss it. And of course, the IBM's representation is the generalization of the Bloch sphere. At the same time, I can notice here that Bloch sphere is not only for for quantum. It is used in many other areas. Of course, spintronics, like spin physics, when we describe the state of a spin, they also use the Bloch sphere. Another area is photonics. All these states, they encode all possible polarizations of a photon. Okay, we will probably discuss this later, but a photon with 2 polarizations is a nice model for a qubit, like vertical or horizontal polarization. They denote the 0 and 1 state. Okay, then plus 45 minus 45 angle degree polarization of a photon represents the plus and minus points in this sphere. And finally, the circular polarization clockwise and counterclockwise photon, it represents the plus I minus I states on the sphere. So the Bloch sphere also used in photonics to represent all possible polarization states of a photon. And finally, you probably, I mean, it's very interesting that, for example, these MRI systems, you know, this medical magnetic resonance imaging, like when you go to hospital, they do the MRI. They also use this Bloch sphere because they also deal with the polarization of a, for example, of a living tissue. Okay, in the strong magnetic field, the tissue becomes polarized, so it gets the vector of polarization. And then what the MRI machine measures basically the evolution of the polarization vector on the block sphere. Okay, so block sphere is very, very useful concept, not only for quantum computing, but also for many other areas. All right. Yeah, so this is basically what we've discussed last time. And today, let me turn off the camera to make it easy for recording. Let us jump to the quantum gates and quantum circuits. So first of all, this is lecture number 7. And the subchapter 3.2, quantum gates and quantum logic. Well, quantum gates and quantum circuits. So, so what is any quantum computer intends to do? A quantum computer intends to run some quantum simulations represented in terms of algorithms. Okay, when you need to solve something, some problem, you need to explain to the computer how to solve the problem. And you explain this problem in terms of algorithm. But in case of the quantum computer, we explain this procedure in terms of quantum algorithm. And the way we represented or explain to the quantum computer the algorithm is a circuit model. Okay, so the circuit model is a sequence of some elementary building blocks that carry out elementary computations. And these elementary computations are named gates. Okay, if you're familiar with the classical computation theory, this is exactly the same terminology. You just add quantum, this word quantum, before gates, before circuit, and before algorithms. Let us write down this statement. So the circuit model, or Q circuit model, is a sequence of building blocks that carry out elementary computations. And these elementary computations called gates. Gates. So you probably know that in classical logic, in classical computation, we have 7 basic logic gates called AND, NOT, XOR, etc. So in classic, we have 7 basic logic gates. For example, AND, XOR, etc. For example, single input output gates, single input output gates. like not gate. So not gate is denoted by this triangle with a circle, input output, some AQ, and 1 in this triangle. And the operation of this gate, as well as of any other gates, is given by the truth table. Truth table. So the truth table basically describes the output in function of the input. Okay, so and for the NOT gate, it basically inverts the state. So for example, if the input is 0, then the output is 1. And likewise, if the input is 1, the output is 0. A nice and interesting point about this type of qubits, this type of classical gates, is that it is reversible, right? For example, if I use it in the opposite way, like replace the input by output and output by input, I still get the same functionality. Okay, so for example, in the direct way, it takes 0 and converts it to 1. But if I flip it, it takes 1 and converts to 0. So it is reversible. So let's note it like not is reversible. At the same time, this concept of reversibility means that if I take, for example, 2 of them, it will do nothing, right? Because the output will be equal to the input. So this is the identity operation. The first one, for example, takes 0, converts it to 1. The second one takes 1, converts it to 0. So you get 0 in the output for 0 in input. Another example, so it was single input, single output. Another example is the 2 input, 1 output. 2 input, 1 output. Gate, for example, XOR. We've got a question in the chat. Is this is all classical stuff, right? Yeah, that's for now. That's classical stuff. I'm just showing you how the gates work in the normal classical computing. And for example, this XOR type of gate, okay, is very useful for understanding the following, specifically the two qubit gate operations. Yeah, this is normal computing logic. Okay, yeah, so another type is 2 input, 1 output. And it's pretty obvious that 2 input, 1 output qubit cannot be reversible, okay, because if the output is just 1, then it cannot work in the opposite, in the reverse direction. So this XOR gate is an example of irreversible type of gate. So XOR qubit is denoted by like this. XOR. It gets two inputs, A, B, and the output Q. And the truth table of this one is denoted, is given by the following. So we have one input, second input, and the result, the output Q, which is equal to the circle plus of both inputs, A circle plus B. Okay. Circle plus what it is. So for example, if the first input is 0 and the second input not change, it doesn't change. So for example, B in the output it becomes B again. If B is 1, then Q is equal to 1. Okay. However, if the first input is 1, then the state of the second one is flipped. So for example, if A is 1, B is 0, then Q is 1. And finally, if A is 1 and B is 1, then the state of the input B is flipped to 0. Okay. So this operation circle plus operation means that if you take a sum of something like this, you as usual get 1, but when you get the summation 1 plus 1, you get 0. Okay, so it's flipped. Circle plus operation. So there are two ways of thinking about this gate. One, of course, is the as classical computing people think about this gate in terms of circle plus operation. Okay, so you take the input of 0 or 1, and depending on the circle plus operation result, you get your output. However, there is another way to think about this one, of this gate, in the way like you use the first input as a control and the second one as a target. Okay, and then depending on the control, you either flip or not the target. Okay, so if A is 0, then you leave the B unchanged. And if A is 1, then you flip the state of the input B. Okay, and this one is not reversible because, for example, if you use output as an input, then you have, for example, 0, you cannot distinguish, for example, between these two zeros. Okay, and if the input is 1, then you cannot distinguish between these two. But there is a way how to make this one reversible. So let us make a note that in quantum computing, all gates are given by unitary operators, and hence they must be reversible. Okay, so in classical computing, we can use reversible and not reversible. Irreversible gates. In quantum, the gates must be reversible because they are represented by unitary operators. So in quantum computing, all gates are given by unitary operators. For example, unitary operator U. Okay, and I just remind you that the unitary operator is the operator that the dagger, the Hermitian conjugated, coincide with the opposite, the in inverse operator. Okay, so the Hermitian conjugation and reverse operator is the same. Why it's so? I mean, just remind you that, for example, if you have a state, some state 0, and then you act this operator on this state, of course you get another state was denoted by psi1 state. Okay, and this operator changes the state somehow, and the only requirement to this changing is that this operation doesn't change the dot product of the state by itself. Okay, so for example, for the bra vector, the bra version of the same vector is equal to this, right? And then and then I take the dot product of the two, and I get what? I get psi 0, then u dagger, then u, and then psi 0. Okay, so I require that this guy is equal to the identity matrix. And if it's so, then the dot product of the both vectors is the same. Okay, if u dagger u is equal to the identity matrix, or if you multiply both parts by the inverse matrix u on the right, then you get on the left side something like this, right? And this is identity matrix. So you get u dagger equal to u minus 1. Okay, so in quantum computing, all gates must be unitary operators. In quantum, all gates must be unitary operators. Okay, so this is the only requirement. So now I'm gonna discuss the quantum gates one by one, and we will use this IBM Quantum to basically example the things. Let me open this IBM Quantum platform. And we start with single qubit gates. Single qubit gates. So single qubit gates are the gates that act only on one qubit. Okay, in contrast to 2-qubit gates, which operate with at least 2 qubits. And there is a theorem in quantum computing that says that basically in order to build a general quantum computer, you need only 3 1-qubit gates and 1 2-qubit gates. Okay, so we're gonna discuss the basic single qubit gates and then maybe just 1 or 2 2-qubit gates, because that's sufficiently enough. Yeah, and we're gonna start with the first one. First is X gate. X gate, sometimes it is denoted by sigma X because it coincides with the X Pauli matrix. Okay, sometimes it's also denoted by PX. Sometimes it's denoted by Q naught, and etc. So in IBM quantum, it's represented by this circle plus. Okay, this circle plus gate. Circle plus gate. So as I said, the matrix of this gate coincides with the X Pauli matrix 0, 1, 1, 0. And in the outer product representation is given by 0, 1 plus 1, 0. Okay, so that, for example, if I consider the state 0 and act this operator on the state 0, what would I get? I get 0, 1 plus 1, 0, and I act on state 0. So this one is 1. This one is 0. Okay, so I get the state 1. So when this gate acts on the state 0, it basically flips it from 0 to 1. Okay, and the same for the state 1. If I take state 1, act the X gate, it flips it to the state 0. Let's check this. So let's go to, let me share my, where is it? Share, yeah. Share my screen. Do you see my screen with the IBM Quantum?
Yeah.
Yeah, so basically, as you get to the system, you go to the composer, which is, so you basically navigate, yeah, this is learning. Instead of learning, you go to the platform. So IBM Quantum Platform, then you navigate to, yeah, to here, basically IBM Quantum Composer. You click here. In your case, it's gonna be empty space like this. So you might have more qubits here. In your case, it might be like something like this, 2 qubits or 3 qubits. I suggest that we, yeah, so first of all, this window here with Q0, Q1, we can add more lines here. So each line represents the qubit. So Q0, Q1, Q2 are different qubits. Okay, different qubits. And anything you do with the qubit is given by these quantum gates here. And as I said, the X gate is given by this circle plus element. So you can add the gates. You can add different gates. Also, what I suggest to use is layers alignment. So layers alignment show the different layers in this quantum circuit. Okay. So you can add the gates, you can remove them. By default, and you can see it here. By default, the qubit is in the 0 state. So it's in the ground 0 state. And if I add this X gate, so by the way, if you right click on any of these gates, you will see this info. Okay, and if you click it, you can basically read about the gate. So I right click on this one, and it shows, and it says that this is NOT gate or Q NOT gate, also known as Pauli X gate. So, and it flips 0 to 1, 1 to 0, etc. So I start from 0 state, and I apply this gate, and it indeed flips my state from 0 to 1 in terms of state vector. And I can also see the probabilities in terms of measurement. Okay, so the state vector represent the eigenstates of the system. Probabilities give me the probability of measuring the system, the states. Okay, so let me go back to the, how do I so yeah. Yeah. But what about, so thus far we discussed the state 0 and 1, but what about the general state? Okay, so the general state of a qubit is given by the angles theta and phi, right? As we discussed last week. So it's going to be cosine theta over 2 state 0 plus exponential I phi sine theta over 2 state 1. Okay, and now I want to apply this state. I mean, I apply this X gate on the left like this. Okay, so what happens is that, I mean, of course, this cosine, exponential, they just constant, right? It's not vector. So we take it out from this operation, and this X gate flips 0 to 1 and 1 to 0. Okay, so what I get in result is cosine theta over 2 state 1 plus e to the power of I phi sine theta over 2 state state 0. Okay. So now I can now I can take this e to the power of I phi. I can factorize it, take it out from the parentheses. So it's gonna be minus, I phi times e to the power of minus I phi, right? Cosine theta over 2, state 1, plus sine theta over 2, state 0. Okay. So now I can use the fact that cosine is a sine of some angle. So cosine of some angle alpha, right, is the same as sine of pi over 2 of the angle. And likewise, the sine of the angle is cosine of pi over 2 of the same angle minus the same angle. Okay, so now I use these formulas to represent this one in the following form: power of I phi times and let me write this one in the first place. So it's going to be cosine pi over 2 minus theta over 2 state 0 plus e to the power of minus I phi sine pi over 2 minus theta over 2 state 1. State 1. Yeah, so as we can see, so we started from the state given by cosine theta over 2 times state 0 plus exponential function I phi times sine state 1. Okay, and and the result of this x gate is again the sum of the two, state 0 with cosine plus state e with some sine. Give me a second. All right. Yeah, with some exponential function. So we conclude that this gate x inverts the general state psi, which means that it rotates it by angle pi, and flips the phase from phi to minus, from phi to minus phi. Right? Yeah. So, for example, in terms of this Bloch sphere, if you have any state like this one, psi, so it flips it, rotates it by pi over x. So, and flips the angle phi. So it's going to be somewhere here. It's going to be x psi, something like this. Okay. And so we already saw that this gate is represented by circle plus in the circuits Sometimes it's also represented by this rectangle with X inside, something like this. So the second gate is Z gate. Z gate. So Z gate is also known as sigma Z gate or PZ gate. Again, that's because different platforms, different books use different representation. In the IBM Quantum, it's given by Z, Z gate. So the matrix of this Z gate coincide with the Pauli Z matrix, which is 1, 0, 0, minus 1. Okay. Or in terms of the outer product, it's gonna be 0, 0, minus 1, 1. So what happens when I apply this Z on the state 0? Again, I get just 0. It's pretty clear, right? What if I applied Z to the state 1? I get minus state 1. So basically, application of this Z state on the state 0 and 1 doesn't change the state up to this minus, which is just the phase. Okay. This is of course not a coincidence, because the sigma Z, this Pauli matrix Z, has the eigen vectors 0 and 1. Okay, that's what we discussed, the spin. 0 and 1 vectors are the eigenvectors of the sigma Z matrix. Okay, but what about the other states? Like, for example, state plus, which is 1/2, sorry, 1 over square root of 2, state 0 plus state 1. Okay, so Z plus is gonna be equal 1 over square root of 2 state 1. No, it's gonna be state 0 minus state 1, because 1 turns into minus 1. Okay, and this is state minus. Likewise, if I apply this Z operator on the state minus, I will get state plus. Okay. And in general case, one can show that the Z operator or Z gate flips the phase. So Z flips the phase, or change it by pi. That's why sometimes it's called phase flip gate. Phase flip gate. Phase flip gate. And in the circuits, it's given by the rectangle with Z inside. Okay, so let us go to the IBM Quantum. Remove this one. Yeah, so and this is the Z gate here. Okay, I can apply it, and of course, if my qubit is in the state plus, sorry, state 0, then applying this Z gate doesn't change anything. Okay, so it doesn't change the state. It was 0, it stays 0. But what if I combine the two? So I apply the gate X to flip my state from 0 to 1. And I expect now that application of the gate Z to the after the gate X will flip the state. Now we see what's happening. Okay, so what changed? In terms of probabilities, nothing. So we still have 100%. But in terms of the states, let me remove it and add again. So it was blue. Blue means the phase 0. Okay. I also check this phase angle to also be able to see the phase. Okay, now I apply this Z gate and the color changed. And this color, this red color, means phase pi. This phase pi is exactly -1 because e to the power of I pi is equal to -1 because of the Euler's formula. Okay. This also shows like one interesting feature of this Q sphere in contrast to the Bloch sphere. The Q sphere or the states on the Q sphere also distinguished or encoded by different colors, and the colors represent the phase of the qubit. Yeah, so let's return back. And introduce the third one, the third qubit, which is, well, Y gate. The Y gate, also known as sigma Y, also known as Py, is given by the matrix of the Pauli Y matrix, which is 0 minus I 0, or in terms of outer product, is going to be minus I 0 1 plus I 1 0. So let's check what happens when we apply this operator on the state 0 first. When I apply on the state 0, this one is equal to 0 because 1 times 0 is 0, and only this one is left. And it's going to be state 1 with this imaginary unit. So it's I state 1. So again, it flips the state from 0 to 1. What happens if I apply it to the state 1? It gives me minus I 0. If I apply this state on the state, for example, plus. Okay, so state plus is what? Is 1 over square root of 2, state 0 plus state 1. And I apply it this Y gate on this. And we just saw that the 0 state becomes 1 with the imaginary unit. So it's going to be I state 1. And then minus I state 0 for the second one. I can take the I from the parentheses. It's going to be I over square root of 2. And inside, it's going to be, and let me take also minus. Okay, so it's going to be 0 minus 1. Or minus I over square root of 2 state minus. Because this is the state minus. Oops. It's going to be minus I state minus. So what we do with this I or minus I, so some number or complex number before the state. Okay, so in this case it is I, but if we recall this Euler's formula, which is e to the power of I lambda, it's going to be cosine lambda plus I sine lambda, right? I can represent the imaginary unit if cosine is equal to 0 and sine is equal to 1. So if alpha is equal to pi over 2, then cosine is equal to 0, sine is equal to 1, and I get the representation of the imaginary unit, which means that states like I minus can be rewritten as I to the power of I pi over 2 minus, okay? And this is known as a global phase factor. And this is not important factor for any computation. Why? Because when you calculate the expectation values for any expectation things, basically something that you can measure in experiment, okay? You need to take the minus and you need to take the product, right? The bracket product or cat bra product, whatever. And when you do so, you take the minus state. For example, for this one, we get minus I pi over 2, right? And then e to the power of I pi over 2 state minus. And this is exactly 1, right? So this global phase factor doesn't change anything. So it doesn't affect on anything that we measure in experiment or anything that we calculate whatsoever. So the factors like this I here, or what it was recently, it was yeah, something like this factor here, it doesn't affect anything. So basically global phase factor doesn't change the things. Only the phase factors that stand, for example, here, only one of the terms in the total superposition affects the result. The global one doesn't affect. Okay. So this is the Y gate. Y gate, what it basically does, it rotates the state around vector Y by angle pi. Axis in the block sphere. by angle pi. Okay, so we're not gonna check this one in the quantum IBM quantum. Let us introduce the another one, which is more important one. So the gate number 4 is Hadamard gate. Hadamard gate. Okay, Hadamard gate. This one is much more important. This one is important because it creates the superposition of states. Okay, so Hadamard gate is denoted by H in all textbooks, everywhere. I basically in all the resources, it's always represented by H. And the matrix of this gate is 1 over square root of 2 matrix 1, 1, 1, minus 1. Okay. And in terms of outer product representation, is given by 1 over square root of 2. And then 0, 0, plus 0, 1, plus 1, 0, minus 1, 1. Okay. And the most important thing is, or action is represented by the following. So if I take this Hadamard gate and act it on the state 0, what would I get? So applying, for example, state 0 here, state 0 here, here, and here. This one canceled because state 1 times state 0 is 0. This one again, state 1 dot state 0 is 0. And I have only two components here. This one gives me state 0. And this one gives me state 1. Okay, so the result will be 1 over square root of 2 state 0 plus state 1. Okay, and this is pretty interesting. So before, I mean, in the input of this gate, I have the state 0, but on the output of this gate, I've got the superposition of two, state 0 and state 1. So this Hadamard gate creates the superposition of states. Superposition of states. Likewise, if I apply this Hadamard gate on the state 1, I will get 1 over square root of 2 state 0 minus state 1, which is exactly state minus, right? And this one is state plus, of course. State minus. So Hadamard gate is a unitary operator, of course, which means that if I take the state plus, for example, and apply the Hadamard gate on it, I will get state 0 back because Hadamard gate is a unitary operator. Likewise, if I take this state minus and apply the Hadamard gate, I'll get state 1. All right, so let us go to the IBM quantum. Okay, and I remove these two. So I start from qubit in the state 0. I see that in here in the state vector representation. And Hadamard gate is represented by this H gate here. So I apply this H gate, and it creates exact superposition of two states, state 0 and state 1. In the Q sphere is given by these two dots on the Q sphere. And what else? No, for example, in terms of probabilities, okay, probability describes the measurement of the things, and we see that if we would measure this qubit after application of the Hadamard gate, we can find it 50% times in the state 0 and 50% times in the state 1. Okay. Likewise, if I start with the 0, I can apply spin flip gate to turn it into state 1. And now I can apply this Hadamard gate right after. And what I get the, again, the superposition of two, but the different color, this red color here, denotes the negative phase. So it's minus 1, 0, -1. So in total, this is the state minus. All right. So let's go back to the clusters. Okay, these are, I would say, the main qubits. Let us quickly introduce the other gates that might be useful. The first one is P gate. aka P1 gate or phase gate. P1 gate or phase gate. So basically, it is generalization of the Z gate. So this gate gets a parameter alpha, and it's given by matrix 1, 0, 0, e to the power of I alpha. Okay, or in terms of the outer representation is given by 0, 0 plus e to the power of I alpha 1, 1. Okay. So let us consider the action of this gate on a general state psi. So this gate is given by this outer product alpha 1, 1. And the general psi state is cosine theta over 2 state 0 plus e to the power of I phi sine theta over 2 state 1. Okay. So all the terms 0, 1, 1, 0 equal to 0 because the states are orthogonal. So I have only the product of these two and the product of these two. So what I get cosine theta over 2 state 0. Okay, so this one doesn't change. plus the second one, which is e to the power of I alpha plus phi, or phi plus alpha, sine theta over 2, state 1. Okay, so all what changed is only the phase, right? So only this phase term changed. That's why it's known as phase gate, because it changes the phase, and all other angles, things don't change. And if alpha is equal to pi, it is exactly Z gate or sigma Z gate. Well, we can also discuss two other gates which are related to this P gate. Let's denote it like a subsection 5.1. S gate. I see it in this IBM Quantum, so it's nice to introduce this one. So you have the whole picture. Okay, so S gate is basically P gate when alpha is equal to pi over 2. This is S gate. So when alpha is equal to pi over 2, it is e to the power of I pi over 2, which is imaginary unit. We discussed this today, right? So it's gonna be the matrix 1 0 0 I. And another one 5 times 0.2 T gate. So T gate is is the same as P gate, but in the case when alpha is equal to pi over 4. Pi over 4. Okay, so it's gonna be 1 0 0 e to the power of I pi over 4. And maybe the last one, the last thing is the concept of U gate. U gate. So the U gate, you can find it also in the operations in the quantum, IBM Quantum. This U gate. U gate is basically the way you can generalize all these single qubit gates. Okay, so if you introduce three parameters like theta, phi, and alpha, you can generalize all the gates we discussed so far just by one matrix. Okay, these elements cosine theta over 2 minus e to the power of minus I alpha sine theta over 2 e to the power of I phi sine theta over 2, and the last one e to the power of I phi plus alpha cosine theta over 2. Okay, so this is basically the most general representation of all the single qubit gates. And for example, if you take U gate with parameters pi over 2, 0, and pi, you will get what? Let's substitute for theta, we substitute pi over 2. So it's going to be cosine pi over 4. Okay. then phi is equal to 0. So this one is gonna be minus e to the power of minus e pi sine pi over 4. T is equal to 0, so e to the power of e phi is equal to 1 sine pi over 4 here. And finally, alpha is equal to pi, so it's going to be e to the power of I pi cosine pi over 4. So cosine sine pi over 4 is equal to 1 over square root of 2. So we take it from the matrix as a common factor. 1 over square root of 2. 1 is here. Then this exponential function minus I pi is given equals to minus 1 with minus, so it's plus 1 here, and this one is minus. So this is exactly Hadamard gate. Okay, and the same way you can check that this type of gate basically represents all the single qubit gates we discussed so far. Okay, so this is basically it about the single qubit gates, and now let us discuss 2 qubit gates. 2 qubit gates. So basically we're going to discuss maybe just one of 2 qubit gates, the most important one. But before, let me remind you about the way we represent the states. So the most general representation of a state of 2 qubits is given by this superposition: C element 0, 0, state 0, 0, C element 0, 1, state 0, 1, plus C 1, 0, state 1, 0, plus C 1, 1, state 1, 1. Okay. These vectors, again, these are the basis vectors in the 4-dimensional Hilbert space. Okay, and the way we write things like this is basically the tensor product of state 0, state 0, right? And also we like, this is the 2 qubit system. We can also sometimes denote that this one belongs to the qubit B, this one belongs to qubit A, something like this. But anyway, we can represent the state of the 2 qubit system using the psi vector, just listing the C elements here. So it's going to be the column vector C00, C01, C10, C11. Right? And as an example of
Professor?
Yes.
I'm so sorry. Could you scroll up just a little bit? I need to catch up. Taking notes. I'm so sorry.
No problem. Yeah. So as an yeah. So by the way, do you have any questions until now? If not, yeah. Example of a state of 2 qubit system is a Bell state, right? That we mentioned last time. So For example, one Bell state denoted like this, phi capital plus is equal to 1 over square root of 2, state 0, 0 plus state 1, 1. Okay, so what it means, it means basically that C0, 0 is equal to 1 over square root of 2, C1, 1 equals 1 over square root of 2, but C0, 1 and C1, 0 equal to 0. Okay, so the same can be rewritten as this. Okay, so this is the Bell state. Or one of the 4 Bell states. Yeah, and maybe last thing to notice here is when we add qubits to the system, of course, our vectors or basis vectors, I mean, the dimensionality is increased, right? And for example, adding like 4 qubits, we would get something like this 1, 0, 0, 1 states, etc. And of course, this is simplified variant of writing this, the state 1 tensor, state 0 tensor, state 0 tensor, state 1. Okay. And this 4 belongs to different qubits, and the way we add new qubits to the system is from right to left. So this is the first qubit in the system. This is second qubit in the system. This is third qubit in the system. This is fourth qubit in the system. I mean, this is the way we usually work with multiple qubit systems. So this is the first, this is second, third, and fourth. Okay, so this is something we will need for the quantum computations. So the first 2-qubit system is known as C-node. C-node or controlled node. Controlled node. And in some sense, it is a quantum analog of XOR classical qubit. Oh, sorry, classical gate. Quantum analog of XOR. It is denoted by the, so now we use 2 qubits. Okay, so I need to draw this line, 2 lines. One is represented, one represents the first qubit, second represents the second qubit. And this C node is given by the element like this. So you see this circle plus, right? And this circle plus element is known as target. And the first one is called control qubit. Okay, so we have 2 qubits. One is known as control, second one is target. And the truth table of this gate is given by the following. So the first one is control, control, second is target. And we have the output. Well, we have 2-qubit input, 2-qubit output, but the state of the control qubit is assumed to be unchanged. So for example, if the state of the control qubit is X, the output is also here, is also X. So it's not changed. What is changed or what can be changed is the target. So let's say if the target is state Y, then the output of the target is this X circle plus Y. What it means? It means exactly the same what we had for this XOR qubit. So if the control is 0, or if the control is 0, the target not changed. So if the target is 0, the output is 0. If the target is 1, the output is 1. And by output, I mean this X plus circle plus Y. However, if control qubit is 1, then the target is flipped. For example, if target is 0, then the output is 1. And if the target is 1, the output is 0. Okay, so in this sense, the state of the control qubit changes the state of the target qubit. Yeah, the state of the control qubit controls the state of the second qubit. And this brings, of course, something interesting to the story. Yeah, so as an example, yeah, so first of all, we can denote this C0 qubit as CX operator like this, okay? And let's consider what happens when when this gate or this operator acts on the state like this 0, 0. So here we have to distinguish between 2 qubits, and in particular we need to kind of remember which one is control, which one is target. So usually, or for the picture like this, the first one is control, the second is target, okay? And here the control is 0, so the target not change, doesn't change. So it's gonna be 0, 0 in the output. Likewise, if my state is 1, 0, then it's gonna be 1, 0 in output. However, if the state is something like 1, 0, 1, and if this one is control, this one is target, then the output is gonna be state 1, 1. Okay. Yeah, let us consider an important example. Known as golden 2-qubit circuit. Golden qubit circuit. I put quotes because this is not something that you can meet in all textbooks. So this golden 2-qubit circuit contains 2 qubits, of course, so 2 lines. Then I apply the Hadamard gate on the first qubit, H here, okay? And then I apply the C0 gate, C0 2-qubit gate like this, with the control upper and the target lower qubit. Let us consider different layers in this circuit. So this is the layer number 1. This is the layer number 2. This is the layer number 3. And the question is, what is the output if the input is 0, 0? Okay. Yeah, so the first layer, the state in the first layer is formed by the tensor product of states 0, 0. Right? zero state and 0 state in both qubits. So it's going to be state 0, 0. With second, this one is control, this one is target. What happens in the second layer? The second layer is the part of the circuit after application of the Hadamard gate on the first qubit. So I write Hadamard gate, Hadamard operator, then this state 0, 0, okay? And now on which qubit I apply this Hadamard gate? On the first one, right? And the first one is this control. This one. So I can split this one as the tensor product of the 0 state in the second qubit is not affected anyhow. Tensor product of the result of the Hadamard gate on the first one. On the first one. So Hadamard gate on the first one, on the 0, it creates the state plus, right? So then the state plus is 1 over square root of 2, state 0 plus state 1. And I multiply, I take the tensor product back. So it's going to be 1 over square root of 2, state 0, 0, plus state 0, 1. 0, 1. So this is the state in the second layer of the circuit. In the second layer of the circuit. Important thing to notice here is that this state is still separable. Separable. It means that I can represent the state as a tensor product of 2 vectors. Okay, so this is the separation of the state into two vectors, 0 and 0 plus 1. So this state is not entangled. It is separable state. But now what happens in the third layer of the circuit? So in the third layer of the circuit, the state in the third layer of the circuit is the state after applying the C0 gate on the state in the second layer, okay, and the previous one. So I write Cx, and it acts on the state 1 over square root of 2, state 0, 0, plus state 0, 1. Okay. So I just apply this Cx on the both states, remembering that the first one here is control, this one is target, control, target. So the first vector control is 0. It means that it doesn't change the target. So for the first one, I write 0, 0. Nothing is changed. But now what happens to the second one? Control is 1. So I have to change the state of the target, which was 0. So now it's 1. So then I get state 1, 1. Pretty cool, because this is now non-separable state. Non-separable state. Non-separable state or entangled state. Entangled state is is not separable state, and this is like truly quantum phenomenon, which cannot be realized, achieved in classical physics. Okay, of course. I mean, the question is what is the physical model for the C0 gate? Probably we will discuss that in what follows. Actually, it's pretty easy to realize something like this using the quantum systems and the dynamics of the quantum systems. In any way, C0 qubits, of course, exist, and they are realized in different approaches, ways. And the existence of these C0 gates allow us to create entangled, fully entangled or non-separable states, which is something fundamentally new. And you can, of course, recognize this state. We already saw this state. It is actually the Bell state, right? So people distinguish 4 different Bell states. The first one is we already saw this phi capital plus is equal to 1 over square root of 2, state 0, 0 plus 1, 1. And phi minus, which is 1 over square root of 2, state 0, 0 minus 1, 1. Okay. I mean, it's easy to see that if this one is created by Hadamard plus C naught, right? The second one needs only the X, right? Yeah, X gate first to flip the first one from 0 to 1, then Hadamard, and then C naught. Okay, so you just change the circuit a little bit and you get this second Bell state. So this is the first Bell. This is the second Bell. And there are 2 other Bell states, psi capital plus and psi capital minus. So psi capital plus is 1 over square root of 2, 0, 1 minus 1, 0. And psi capital minus is 1 over square root of 2, 0, 1 minus 1, 0. Okay, so this is third Bell. And this is for Bell state. You also can come up with the circuit for this Bell state representation. Okay, let us go to the IBM Quantum and actually check that we've got, I mean, our check our calculations. Check our calculations. So first of all, our circuit now is 2 qubits, so I need to add another qubit here. Okay, I added second qubit. And let's actually first check the order. So if I flip this, so now the space is 4-dimensional, right? So we have these 4 different state vectors, 0, 0, 0, 1, 1, 0, 1, 1. And by default, it starts from the state 0, 0, when the both qubits in state 0. And then when I apply this state flip qubit, gate, it flips the state, but from 0 to 1. And we notice that it is the flip of the first one. Okay, so it's 0, 1 now. And if I apply it to the second one, it's gonna be 1, 0. So it's 1, 0. Okay. So the order here is it matters. Okay. So now I can apply this Hadamard gate to the first qubit. Okay. Before that, so our state is 0, 0 in the first layer of the circuit. You can check that compared with our calculations. Then in the circuit, in the second layer, we get the superposition of 2, 0, 0 and 0, 1. I can hide the 0 states, so they yeah, so basically we have the superposition of 2, 0, 0, 0, 1. They are with the same phase, angle 0. And this state is separable because I can represent it as a product of state 0 and state 0 plus 1. And now I can apply this C0 gate, denoted like this. You see this circle plus with this element here. The upper is control, the lower is, the second is target. And we see that now the state becomes, the resulting state in the third layer is 0, 0, 1, 1, which is not separable. 0, 0, 1, 1. This is the first Bell state, the generation of the first Bell state. Let us check the second Bell state. So when I expect that when I apply this X gate to flip the first qubit, it will create me the same states, but the second one will be red because the phase will be flipped by angle pi. Okay, so let's check that. Add it here. Yeah, so the angle is flipped by angle pi. So this is basically confirms our calculations. So what is important about this golden 2-qubit gate is that, for example, you have a system and you receive some sort of entangled quantum states. Okay, so you receive quantum states generated somewhere, somehow. So let's assume that this part of the circuit generates the entangled states that you receive them. So, and you can use this circuit in reverse to split the states to the initial ones. So what you do, you just do the same, but in the opposite order, right? You apply this C node and then Hadamard, and your result is state 0, 0. So 0 here, 0 here. If you first apply the X flip here, this golden 2-qubit gate applied in the reversed order resolves the initial state 0, 1, etc. So this golden qubit gate, golden 2-qubit circuit, not only allows us to create entangled states, but also allows to decompose the entangled states into the states, the four-week states. Okay. Yeah, so this is basically it about this part. We will continue next week. And we will start doing some like more interesting simulations also next week. All right. So thank you very much. Do you have any